It's my very great pleasure to introduce Max Gunzburger. Max is the editor-in-chief of the SciAm Journal on Uncertainty Quantification. Is an extremely prolific and highly cited author. Has graduated 37 PhD students. I believe you said, yeah, 36 of whom are still doing research, which is incredible. I first met him only a few years ago at the University of Otago in Dunedin, and he gave a great talk there, and I'm expecting and hoping that he'll give a great talk here. Take it away, Matt.
Thank you very much. I thank the organizers for inviting me to this conference, which has been quite fascinating. So yeah, I'm gonna, I know the Wizard of Oz. If you wanted a brain, all you needed is a diploma. And if you want to be an expert on UQ, you're editor-in-chief of a UQ journal. It doesn't mean you really know anything. But anyway, I'm going to talk about UQ, uncertainty quantification. I can never answer this question because I can never finish the Tootsie Pop without biting on it, and I never get to the core. But anyway, uncertainty quantification. So, since this conference, when I was invited, I tried to talk my way out of it because I was afraid I wouldn't fit. But anyway, I decided, I asked myself the question, what happened to the term natural philosopher? Because you hear that all the time about the olden days, but not now. This is a town in Texas, near a town called Uncertainty. So I found out what happened to the term natural philosopher. In 1833, there was a meeting of the British Mathematical Association, and one of the two attendees of the meeting were the poet Samuel Taylor Coleridge. You may not know that he actually wrote a book on the philosophy of science. And there was a remarkable man called William Whewell. And at that meeting, Coleridge sat in the audience and listened to mathematicians get up and give talks. And a lot of them started giving talks about going out in the field and making observations, and then, or partnering or doing laboratory experiments, and then coming back and trying to do some math. And he was appalled by this. And he actually got up and said, "You no longer have the right to call yourselves natural philosophers." So William Whewell was a wordsmith. Among other things, Faraday asked him to help him name some things. So Whewell is responsible for the words anode, cathode, dielectric, and various other things. He was one of the most influential people in British physics and mathematics in the 19th century. So at that meeting, Whewell said, "Well, we need a new name." And at that meeting, he coined the word scientist. He also coined the word physicist, by the way. So it took 50 years for scientists to catch on, by the way. They didn't catch on right away. But that's what happened to natural philosophers. They became scientists. Well, since my talk may not have much intelligent to say, I decided every now and then during my talk I will make some quotes from intelligent people, like Voltaire. So what is uncertainty quantification? Well, first of all, let's answer who does uncertainty quantification, and that's everybody. No matter what field you're in, there's somebody doing uncertainty quantification, or should be doing it. By the way, I have several of these small font things, which are usually snide remarks, which does not apply to anybody in the audience, of course. And so I decided also that since Whewell liked to use ists, maybe we should call ourselves differential equationists or appliedists. Now, why does everyone want to do UQ? Well, in the US, there's money in it. It's become a lemmings going over the cliff syndrome that one funding agency or one person in one funding agent decided the QQ was important and funded it, and then the other funding agency said, well, if she thinks it's important, we better fund it. And so there's lots of money for UQ. So that there are a few people who actually are doing it because it's interesting and important. So of course uncertainty is everywhere, and mathematical models should reflect this. And as you all know, mathematicians or scientists like to use Greek as opposed to lawyers and doctors and biologists who try to classify biota, who use Latin. So they coined these words for epistemic, to classify uncertainty that comes from incomplete knowledge, and which can in principle be reduced by doing more experiments, and aleatoric, which cannot be reduced by doing new experiments. To be frank, I always had trouble figuring out which is which, and certainly the boundary between the two is very fuzzy. And here's a quote from the Wikipedia article on UQ. Indeed, it's a philosophical question as to whether aleatoric uncertainty is even a meaningful concept. I'm coining a third world called computational epistemic, because people throw in, for instance, randomness into models because they're trying to model, as was discussed this morning, scales that they cannot model, get onto a computer. In other words, if they try to model down to a really small scale, they will not be able to get any results. So what they do is they have to do some modeling to either parametrizations, that's what it's called in several areas. So they artificially introduce, for instance, uncertainty in the system to try to model the effects that the small scales have on the large scales without actually having to solve for the small scale. But little point. So everyone thinks laboratory experiments are not repeatable. Everybody thinks computational experiments are repeatable. And it is true that unless you're kind of a fool, that if you run the same code with the same inputs on the same computer, you should get the same results both times. But if you run the same code with the same inputs on two different computers, you do not necessarily get the same results. And in fact, sometimes it doesn't run at all. So even computational experiments. So what's a complex system? Well, I think complex system was invented because when you write a proposal, it's a lot better to say you're working on complex systems than on simple systems. So I don't really know where that was invented. My definition of a complex system, well, it's in the eye of the beholder. To me, function evaluations or integrating a known function is not a complex system. Navier-Stokes equation is a complex system, but my definition is that if you put it on a computer, it takes a lot of computer costs to get an answer. That's my definition of a complex system. So throughout this talk, function evaluations are going to be expensive. And that makes life hard because theorems that say something converges as a number of samples going to infinity are useless because your number of samples is going to be 15. Okay. Here's another quote from Pascal. After yesterday's talks, I couldn't resist putting in a little something on simulations, which comes from simulate. And the OED defines simulate by these two definitions, which basically says to simulate is to cheat. It does go on, and its fourth definition is to produce a computer model of a process. Also, leading from yesterday's talk, I want to put in this famous quote by George Box, great statistician. All models are wrong, but actually before, this was actually the title to a section in a paper, and a few years before he actually had this quote, which is very much in line with some of the things we've heard this morning. So, simplicity, he likes simplicity just like the people this morning pointed out. There's another quote which I've never been able to find the original source, but it's also quite famous, that experimental results are believed by everyone except by the person who ran the experiment, and computational results are believed by no one except the person who did the computations. Very true, by the way. How do uncertainties enter into a system? Well, there's model form uncertainty. I think maybe this is what we call structural uncertainty this morning. I don't know. You don't know whether what terms are in the model. This to me is the hardest thing anybody can do, is figuring out what terms should be in a model and what they should look like. I don't pretend I can do that. We've heard a lot about model parameter uncertainty, where you have some parameters in the model and you want to find out what they are. And for me, of special interest is function inputs, inputs that are functions, for instance, coefficients that depend on x, or right-hand sides that depend on the independent variables. Try to figure out what those are. So what is uncertainty quantification? And, well, I'll tell you what it means to me by a series of sketches. So, to me, uncertainty quantification is, you got uncertain inputs, you got information about those inputs, find information about uncertain outputs. And in between there's this rectangle called a system, which maps uncertain inputs to outputs. Well, I'm going to keep on narrowing this down. First narrowing down is a system to me are PDEs. So, same definition, but now the system is replaced by PDEs. And invariably, you're not interested in the solution of the PDE itself, but you're interested in something that depends on the solution, a functional. Like, you're not interested in the flow field at every point around an airplane. You're just interested in the lift and drag on the wing, for example, which is a functional of a PDE. So there's another rectangle. You solve the PDE, you have an uncertain solution, and then you post-process it to get some quantities of interest. And finally, there are many different ways to characterize uncertainty. I'll list some of them there. But I'm going to talk about probabilistic characterization. So the final thing is I have statistics about the inputs that I know. And in the end, I want to know statistics about some output of interest that depends on the solution of the PDE. It seems we're in business. Someone from on high gives us a mathematical model and statistical information about the inputs of the model. And then to obtain statistical information about solution of the model, all we have to do is devise a means to solve the model equations. Small problem. Someone on high disappoints us. Often we do not have the slightest idea what the statistical information about the inputs are. So the most common approach is to make an educated, but more often than not, out of the blue guess as to what is that information, and what can do some better, try to use laboratory or field observations to make a more informed guess, keeping in mind that these observations come with uncertainty, a fact that is often ignored. And so this leads to model calibration, which we all know about, which includes parameter identification. And this is so here's a direct problem, and here's the model calibration problem. We all know about that. And this is a special case of something that interests me, which are, in general, stochastic optimization problems, where you have a system and an objective, and you try to determine an optimal control. So your output is some optimal control and optimal system states, or also feedback controls, which all could be done under the aegis of uncertainty. Even poets seem to move to uncertainty. Anyway, okay, let me discuss two great divides. The first one in uncertainty quantification. The first one is probability and analysis. I used to be editor-in-chief of SIAM Journal of Numerical Analysis, and I started getting papers on stochastic PDEs. So at that time, I didn't know anything about stochastic PDEs, not even the epsilon I know now. So I named some probabilists, somebody who came to stochastic PDEs from the probability side. And unfortunately, the papers that were submitted were from people who got the stochastic PDEs from the analysis side, or the numerical analysis side. And all the papers were rejected. And I finally figured out what was going on is that there is a big gap. Probabilists who study complex systems tend to have a narrow view of of uncertainty, and therefore narrow characterizations. For instance, the term stochastic PDE. Now, to me, being from the analysis side means a PDE with random inputs. To most probabilists, the stochastic PDE is a PDE driven by additive white noise. That's it. So, and that was one of the problems. On the other hand, analysts often pay lip service to probability, and that's probably because they don't know any. So you will see many, many papers in journals which says that F, B, and P be a probability space where F is this and P is this, and omega is a sample space. And that's the last time you hear any of that in the paper, but they have this paragraph there, trying to show that they know a little probability. Okay, next great divide, statistics and applied math. As I told somebody, at least in the US, if you want to get punched in the mouth, go up to a statistician and say, statistics is a branch of mathematics. Interesting enough, as I was doing research, I thought statistics was a relatively modern, separated. I was one of these people who said that, not in front of statisticians, of course, but and I really believed it. When I was making the research on natural philosopher and the British Mathematical Association, I found out that this association had sections. You know, they had sections on different areas of mathematics, and they had a separate section on statistics even back in the 1840s. So they recognized that it was, but they still was in a math society. So statisticians wonder what the recent and growing UQ buzz is all about. I've had statisticians tell me, well, statistics and UQ are synonymous. This is what we do. It's true. Statistics is about quantifying uncertainty. And certainly statisticians like to tell mathematicians that we know everything. You developed a method, well, we've known that for 54 years. And, but first determine if their methods are really applicable to complex systems. Of course, applied mathematicians do not believe statistics can tell them anything about complex systems. And as a result, they ignore statisticians and the statistics literature, and they keep on reinventing the wheel. Fortunately, the UQ divide between applied mathematics and science, and especially engineering, is much smaller. If time permits, I'm going to say a few words about interdisciplinary research apropos of this. So what are the types of noise? Random parameters. Well, think of this as knobs in an experiment. You know, you say, I want to have this certain voltage, so you turn a knob to this voltage, but of course, it's not exactly the voltage you think you're turning it into. So that's a simple way to random parameters. So we've heard about them several times, things like Young modulus, diffusivities, speeds of sound in models. Then there's our old friend white noise, which means that if you have space-time white noise, at every point in your domain and every instant in your time interval, you sample from a given PDF independently from any other point and any other time instant. So these are uncorrelated random fields. A lot of the work in numerical analysis and applied math is about correlated random fields, where they're just like these again are random. Is a function that has a random value at every point and at every time instant, but the points are not independent. The idea being here, if I'm standing here and it's raining, it's indoors, let's say, and or maybe the sprinklers are going, and chances are he's getting wet too. So white noise says, well, chances are he's not getting wet, while correlated random fields, if he's close enough, it's going to say Rob's getting wet. So here's white noise, and approximate realization of white noise. And here are two realizations of something called pink noise, and two realizations of brown noise. Brown noise is Brownian motion, Brownian noise. Pink is called this because its power spectrum is halfway between this and this. This is 1 over f to the 0, this is 1 over f squared, this is 1 over f, and in some circles brown noise is called red noise, and that's why this is called pink noise. Well, what's wrong with white noise? It's ubiquitously used. Like I said, that's what, for instance, probabilists do everything about. There's a problem with white noise. Its spectrum is flat, so it has infinite energy. So it cannot exist in nature or anywhere else. There's no such thing as natural white noise. There's probably truncated white noise, but not natural. But people do that. So you cannot implement it on a computer exactly. So why do people continue using it? Well, because it's trivial to implement, trivial to discretize and implement. And the other reason is that for many equations like elliptic and parabolic equations, the solution is much, much smoother than the noise. So for instance, here is basically a solution of uxx equals f, where f is white noise. So the input looks like that, the output looks like that, nice and smooth. So what you got out of the computer looks nice, has finite energy and all that, but you know, because things are smooth. Colored noise, so colored noises are ubiquitously used, but they really don't exist. Colored noises are ubiquitously present, but are seldom used, at least in the PDE setting. For example, we all know about Brownian noise, which is diffusion processes. Levy noises are also are related to stochastic processes, but they're processes with jumps, and leads to this big field of anomalous diffusion, which is a popular field in Otago. Ornstein-Uhlenbeck noise is a very popular noise in the sense because it's a mean reverting process. You do lots of stuff, but in the end, the solution reverts to its mean. The most used noise are fake noises. When one doesn't know the nature of the noise, one assumes or guesses a correlation function like a Gaussian correlation function or an exponential one where you only have the first power. There's all sorts of correlation functions that are used, and people try to justify them, but basically they're just guesses. So here's something just from the Wikipedia article on pink noise. All the places, pink noise was first observed by Johnson, who was studying flicker in vacuum tubes. He was just measuring the flicker frequency in vacuum tubes, and he found out that the frequency, the spectrum was like 1 over the frequency, decayed like 1 over the frequency. And in fact, pink noise is called, in some circles, it's still called flicker noise. And so there are all sorts of application, including brain, arrhythmic in the heart, you name it. Somebody did an analysis of Bach's Brahms Concerto No. 1 about certain features of it and found out it's distributed as pink noise. Here's Karl von Clausewitz, the famous military strategist. Okay, let's see, how am I doing here? Gotta speed things up. Okay, now, so we started with random parameters. We moved to white noise fields and colored noise fields. Colored noise fields are a problem because you're not usually given a formula. You're not given, say, you have a function of eta, you have a function of x, maybe t, out of a random variable, but you're not given that formula. All you know is that if you want the value at a point, you sample a PDF, but you have to keep in mind there's a correlation structure, so you just cannot just sample it and go away. With white noise, you can do that because every point is sampled independently. But you can't do that with color noise because there's a correlation function you have to worry about. So what do? So white noise and colored noise are infinite stochastic process. So that means there's an infinite amount of information that you have to provide a computer to be able to model it, but of course you can't do that. So you have to do something, you have to discretize both white noise and colored noise. White noise, there are different ways to discretize it. The simplest way is if you're solving a partial differential equation, you have a grid. At every grid point, you sample the noise independently of what you sample at any other grid point. Or if you're doing finite elements, you would have a grid cell. You would sample a different value of the noise at each grid cell. So here's, for example, with different spatial grid sizes, samples of discretized white noise, piecewise constant white noise. So you see it goes up and down randomly, but of course this is a lot smoother than that one-dimensional picture I showed you, because everywhere in this triangle, the value of white noise is the same. And there are theorems that say what happens as h goes to 0, that the correlation function for this does converge to delta functions as h goes to 0 in some sense. And here's two different times, but anyway. So in colored noise case, you can use grid-based discretizations, but they're not usually used because they're hard. So people instead, you could write infinite expansions in terms of orthogonal functions. The most popular is coherent-Levy functions, expansions, which come by many other different names, as we rediscovered as PCA, as POD, and many other names. Our polynomial chaos expansions, which basically use orthogonal polynomials. So you have these infinite expansions, you truncate it, then you have a finite number of random parameters, and you're off to the computer. So here's a realization of approximated colored random field. This is what's called a Reese field. Big difficulty about random inputs 1, which comes with some under the rug sweeping. So far I've tacitly assumed you know the PDF and you know the correlation function, so you could do KL expansions, for example. Well, in practice you don't know that. So you're lucky if you know a range for the values, in which case everybody assumes, well, it's uniform in that range. Or maybe if you're lucky, you know mean and variance of the input parameter. So, okay, mean and variance, I'll say it's Gaussian. A little problem with that. Here are two PDFs with the same mean and variance. So if all you know the mean and variance, but you know, as we all know, Gaussian PDFs is the only PDF that's completely determined by the mean and variance. Every other PDF, you've got to know skewness, kurtosis, and all the other moments. So, of course, this leads back to the stochastic calibration. Big difficulty number 2 is a little more under the rug sweeping. So if you have a colored noise, well, input variables could be independent or jointly distributed, or could be correlated or not. And people mistake uncorrelated with independent. So for instance, the Carhunian-Low expansion does two wonderful things for you. It gives you a formula. In other words, it gives you an expression for the random field as a sum of linear sum of functions of space and time times random parameters appearing linearly. And if you truncate that sum, you have a formula you can evaluate to determine the value of the random field at every point and every time. The other wonderful thing it takes is it takes a correlated random field and writes out that sum involves uncorrelated parameters. So it's a wonderful thing. What it does not say is it gives you independent random parameters. And here's the classical example. Y1 is uniformly with a center distribution uniformly distributed. Y2 is equal to Y1 squared. Obviously Y2 is not independent, but the correlation between Y1 and Y2 is 0. So the only time you can assume uncorrelated implied independence is if your distribution, if your multidimensional distribution is what's called multivariable Gaussian. In other words, it's a product of one-dimensional Gaussian distributions. Otherwise, and that's an if and only if statement, by the way. Okay. I'm doing great. I'm going to go right into the Okay. So what are the outputs of interest? Well, the solution of the PDE is not usually something you're interested in, as I already said. And until yesterday, I didn't think anybody would ever be interested in individual realizations. But now I understand that at times there are interest in individual realizations. What are the outputs of interest? The outputs of interest are statistical information about your PDE. Ideally, you'd like to know the whole PDF of your outputs, but most of the time you're happy with finding expected values and variances. And you're not interested in statistical information about the solution. You're interested about some function of the solution, like the drag or things like that. So anyway, I'll let you read this and move on. Now we have the curse of dimensionality. This is very popular terminology in applied math. So as a numerical person, I'm very used to knowing that 2D is harder than 1D, and 3D is harder than 2D when you're trying to do a computation. And there are applications of PDEs where you have 6D plus time, and there's even some now we have an infinite number of PDEs, but those are kind of esoteric. But anyway, I'm used to 3D being really tough. Well, now, not only do I have to discretize 3 space variables, I have to discretize a parameter domain. It's usually a hypercube. or an infinite domain. And if you have n parameters, it's in Rn. So you have to do discretize in space 3 and in parameter space n. So you have 3 plus n dimensions that you have to discretize. There's no derivatives in the parameter things, but you still have to approximate in the parameter space. Maybe you have time. Well, as we saw yesterday in Professor Senserna's talk, things could get bad. So let's talk about interpolation of in total degree polynomials. So the highest degree any term has is p. The sum of the degrees is p. So you can have y1 squared and y2 squared, but you can't have y1 squared times y2 squared. Or tensor products, where you can have products where each individual parameter, the highest degree, has to be p. Both of these have the same approximation properties in the sense that interpolate the same degree polynomials exactly. So here's the complexity. This is following up on Professor Senserna's table. So very modest, 20 parameters. You only go to third degree. These are global polynomials, by the way, third degree global polynomials. Using tensor products, you have big more than 10 to the 12th unknowns. You do a lot better with total degree, but if you have 100 parameters, you want to go to 5th degree, it's still pretty big. So that's the curse of dimensionality. It's explosive growth as the degree of the polynomial and especially as the number of parameters grows that you have to deal with. Okay. So how do you approximate solutions of PDEs with random inputs? Some lingo. Stochastic phi element method. This is what most of the papers are about. At least the ones that pretend to do rigor. And many of them are pretending. You use phi elements for your spatial discretization. You have a PDE with random inputs, and you use phi elements to do spatial discretization. Stochastic Galerkin method is one where you also use a Galerkin method to affect discretization with respect to the parameters. So you have a variational problem, you integrate grad u dot grad p over the spatial domain, but then you do another integral over your parameter hypercube, and you have to integrate times rho of y, the PDF, times y, which is a vector in Rn. And stochastic sampling methods, the PD is solved at each of a set of sample points in parameter domain. So stochastic Galerkin methods. The good news is you only have to solve one problem. You don't have to do any sampling. You just solve one problem. It could be nonlinear if your PDE is nonlinear, but you solve one problem and you get an answer, u as a function of x, t, and y, your parameters. There's no need for sampling, and you can evaluate that result any way you want because you have a function. The bad news is that the physical and parameter degrees of freedom are coupled, so your signal system is Jn times Jm. J is your phi element degrees of freedom, that could be 1,000,000. M is, on that table, could be 1,000, 1,000,000. So that's how big a system you have to solve. And if your PDE is nonlinear, there's nothing you can do, that matrix will be full. With linear problems, you can get away with something. There are ways to get away with that. So the usual way to do approximations is to do it in terms of orthogonal polynomials. And you may have heard this terminology. This unfortunately goes by the name of polynomial chaos. It took me a lot of time to figure out what polynomial chaos meant. I started reading Wiener's paper. He's the guy who coined that phrase, but he was doing white noise, and expansions of white noise. And then it finally dawned on me that polynomial chaos is nothing more than global orthogonal polynomial approximation. I wish they had called it that. I was a little dense. It took me quite a while to figure that out. But that's all it is, global orthogonal polynomial approximation. Stochastic sampling methods. You just pick endpoints in parameter domain. You solve your PDE at those endpoints. You use those M solutions to build an ensemble average of whatever you want to do. And And so to determine statistical information, you just have to solve n finite element problems. So you have to solve n problems of size j by j, m sparse problems, because they're n finite element problems of size j by j, while instead of one problem of size mj by mj. Of course, the list of sampling schemes is very, 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 I probably needed at least 3 or 4 more, very long. The most popular in practice is Monte Carlo. You all know what Monte Carlo is. You do your sampling randomly, either according to the PDF or not. The good news, the convergence rate is independent of dimension n. This is about the only method whose convergence rate is independent of the number of parameters. So this is the only method that beats the curse of dimensionality. More good news. Monte Carlo does not care about the smoothness of your solution or of what you're approximating. You can have jump discontinuities. And so the bad news, its convergence rate is slow. More bad news, more sampling does not necessarily make the error small. It's not, you don't have any monotonicity in the way it converges or doesn't converge. So this gives rise to quasi-Monte Carlo methods. So, nearly sort of Monte Carlo methods. Not, you got to play poker with dogs, not with rich Europeans. So this is a huge industry. Approximate sort of Monte Carlo methods is a huge industry. The list goes on forever. Forever. And yes, for example, a lot of these methods have a convergence rate which is log of the number of samples you're taking raised to the number of parameters plus some constant s divided by n. So instead of 1 over square root of m, you have 1 over m. Hey, that's wonderful. Except log m to a power swamps 1 over m. Doesn't take long for log n to a power to swamp over m, so this suffers from the curse of dimensionality, even for moderate n. So what about better quadrature rules? Better quadrature rules. So everyone knows that in one dimension, if you have a smooth function, Gauss rules are better than Monte Carlo, as we were told yesterday, very, very elegantly. And this is why in low dimensions, tensor product, like if you're doing phi elements and you're using quadratic elements, a lot of people use Gauss quadrature rules in 2D and 3D to evaluate the integrals in the phi element systems. Because in 2 and 3D, tensor products are okay, but we already saw in my table and also in Professor Sancerna's table that has explosive growth as the dimension increases. And you can fill in. So tensor products should be avoided like, I don't know, you could say the plague, your mother-in-law, whatever you want to So what about interpolatory rules based on total degree interpolation? Well, this is an interesting fact, is that the theory of good points for interpolation is one of the most elegant, beautiful theories there is. And unfortunately, it's a 1D theory. Almost very little is known about good points. Like we all know the Chebyshev points are better than the uniform points in the sense that they have a small elevated constant. But those kind of results don't exist in multi-dimensions. So you want to do a quadratic polynomial on a square. 6 points you need for a quadratic polynomial. Where do you put those 6 points? Nobody knows what's a good place. You don't have symmetry or anything like that, because you can't fit 6 points with symmetry. So, but this is something that lots of people are looking at, including myself. You don't know good quadrature points. Then along came Smolyak. Well, I tried to find a picture of Smolyak on the web, and this is what I found. I didn't find a picture of Sergei Smolyak. This is a Russian country band named Smolyak. And these are 2 random Smolyaks. Sergei Smolyak did a wonderful thing. He figured out a way to take tensor products grids. Tensor product grids are overkill. You have a lot more points than you need to integrate a certain degree polynomial exactly. We all know the triangle. total degree, you put 1, x, y, x squared, x, y, y squared. So you have the total degree in this triangle, and then the tensor product fills in this. Well, as the degree of the polynomial increases and the number of independent variables increases, this thing gets really, really big. So Smoljak figured out how to keep a relatively small amount of what's under here and still get the precision not lose precision. So you can't really exactly count the number of Smoljak points, but it grows this way instead of that way. So he did very good, and so these are what Smoljak grids are, but there's still more points than you have in the total degree triangle. Remember, total degree was good, it was only good relative to tensor products. If you didn't know about tensor products, you think total degree was terrible. So here's a Smoljak grid. That 65-point sparse grid that doesn't integrate the same as a tensor product, filling in all of these lines as a tensor product, but it does much better than any tensor product grid that has less than 65 points, much better. Notice there's lots of holes here. So sparse grids work the same as polynomial chaos, only if you have smooth solutions. If you use orthogonal polynomial approximation, you're only going to get good answers if you have a certain number of derivatives, or else you're wasting your time using high degree polynomials. Same with sparse grids. You're wasting your time if what you're trying to interpolate or integrate is not smooth. Because the only way you can fill in these holes is that if things are smooth. So here's the thing, the difference between sparse grids for a function that has a jump discontinuity, the integral of a function with a jump discontinuity. You see the sparse grid error. This is the exact value. You get garbage. Well, Monte Carlo, with this many, these numbers are, you cannot exactly pick the number of sparse grid points. They're picked for you. So that's why these are strange numbers. But the same number of Monte Carlo simulations gives you that. Notice the non-monotonicity, which is troubling. So where are you going on uncertainty quantification? Actually, I don't have the slightest clue. But so what you do is what the Captain Louis Renault did in Casablanca. You round up the usual suspects. Here's some advice to all you young people. Any proposal you write, put at least 4 of these words in. At least 4. I put in multigrain because I like multigrain bread. So I'm trying to use it in the proposal sometimes. Anyway, adapt. So what are people doing? Total degree is not good enough. It's too many. So what you want to do is, but that's the best you can do if you don't take the function you're interpolating or integrating into account. Because all total degree says it integrates a certain number of polynomials. It's the least number of points you need to integrate or to interpolate or whatever a certain polynomial space. That's all I can tell you. But as you know, for instance, in 1D, that gives you the Chebyshev points if you ask that question. But as you all know, if you're interpolating a periodic function, the uniform grids do much better. A uniform grid does much better than Chebyshev grid. But you're taking into account a property of the function. So here, people are doing this adaptively. I don't know what the state of I want to know what the state of uncertainty quantification is in China because I'm trying to find a partner to make a proposal for a bank meeting. But the state of, as far as rigorous mathematics, Germany is like, and France and England are way ahead of the United States. Almost no one's doing rigorous math. So we do adaptive sampling. So we try to take advantage of, do some sampling, solve your PDE for those samples, and use those solutions that you just found to determine what the next sampling point will be. And there's lots of things you can take into account. Adaptive sampling. Anisotropy is something you have to take into account. Not all parameters need the same resolution. Some parameters don't have much influence. You don't want to waste a lot of points. You also want to screen parameters. There are ways you can try to figure out a priori or as you go along which parameters are not important you can just throw out. People are drawing things like comprehensive and other ideas from signal processing. So the whole idea is to get a certain approximation level. The ideal is, given an epsilon, find me the best m-term approximation. In other words, what is the fewest points I can use, and tell me where those points are to give me an error epsilon that somebody's given me. So this is what adaptive sampling is doing. Surrogates. So most of the work going on in UQ is about trying to do more efficiency in parameter space. Remember, function evaluations are really expensive, so you want to cut down the number of samples, or you want to cut down the number of terms in your polynomial chaos expansion, etc. But maybe you could do something to cut down the cost of obtaining those solutions of the PDE. So people are into making surrogates. In other words, you do some solutions of the expensive filing code, and then using those solutions you build a surrogate in parameter space. Interpolants, least squares. There's such a thing called greedy algorithms, which again determine points at which you're going to build your surrogate. POD is another way to build surrogates. So they're building low-dimensional surrogates. You pay the price of a few expensive samples of the solution of the PDE or of your quantity of interest, and then you build an interpolant, and then anytime you need more samples, you evaluate the interpolant, which is free, compared to solving another PDE. So building surrogates is a big industry these days. Of course, inverse problems is a big problem, and I'm not talking about not just model calibration, but optimization and control problems where you have stochastic inputs, so you need stochastic controls to stabilize that thing. So there's a common mantra that because so much progress has been made in solving PDEs, that now we're ready to do inverse problems. Well, I worked in control and optimization of deterministic control and optimization for many years, starting in the 1980s, and this same sentence was said then, that well, now because we can do the direct problem so well, let's start doing the inverse problem. And that wasn't true then about deterministic problems, and this is certainly not true now about stochastic problems, but still, it's not bad to do it. So there's all sorts of approaches here. Bayesian approaches are pretty seductive for this, but direct optimization approaches are also good. But the stochastic PD, so the stochastic setting needs some more thought as far as even posing the problems. For example, most people take you're minimizing a functional, you're doing an optimization problem. So you have a deterministic functional, and people just then say, okay, I'm going to wrap around an integral over the parameter space. So they're taking the expected value of a deterministic functional. Is that the best way to do things? We just finished a paper that says it's better, for example, to take the, instead of taking the norm of u minus some target u, let's say squared, integrating over your domain and then integrating over parameter space, it's better to take the norm of the expected value of u minus the expected value of parameter. So there's some thought needs to go into that. Rare events. So rare events is something that happens rarely. That's the definition. So this is a big area. It's very hard. There's lots of work, but this is still a good area to get into if you're willing to be disappointed. So it may not be a good area if you're waiting for tenure or something like that, because it's very hard. Because you're either working, there's two kinds of rare events. You're working in the tails of the probability distribution. So if you're doing sampling, you're never going to get any samples when you need them, so you got to do something like important sampling or something to get out there. The other kind of rare event is you're in the high probability region, but the rare event only happens for a very narrow band of parameter values. And that one no one looks at all, because then in parameter space, you have to identify a small region and sample in this little region. And nobody knows how to do that. So this is an open area. Risk is an important, maybe the most important area of UQ. So by risk I mean, suppose I give you a functional f of u, depending on the solution of the PDE, and I ask you to find the probability that f of u is bigger than 7. And if it's bigger than, and the reason you want to ask that, because if f of u is bigger than 7, the bridge you just assigned is going to fall down. So you want to know what the probability of f of u being bigger than 7. Well, that's the integral of the characteristic or indicator function of f of u bigger than 7 in parameter space. Well, you don't know where that region is because you've got to solve the PDE to evaluate f of u. And usually, you're looking for small probabilities. Hopefully, you didn't design a bridge which has a 50% chance of falling. So you're hoping you design a bridge that has a 99.99% of not falling or higher. So again, you're trying to identify small regions in probability space. So this is a completely open area. And in these type of, the problem here is exacerbated by the fact that you're integrating a characteristic function which has jump discontinuity. So all these methods that people have been working ad nauseum, polynomial chaos, stochastic collocation, are useless because you're basically integrating a discontinuous function. So there, Monte Carlo still beats everybody because it doesn't care whether the function is continuous or discontinuous. So what is needed is not new problem areas or new ideas. We have plenty of new and old bad ideas, but we need new good ideas. And we do need more mathematics. So I'm an advocate that mathematics will play a big role. Two things I do know, we're never going to know how many licks to the center of the Tootsie Pop. And we're not going to do problems with 1 million significant parameters in my lifetime. And the reason I put this quote is because a recent call by a funding agent in the United States required you to say how in 5 years you're going to do 1 million parameters. Shows you how much they know. So I responded to that and told them I'm not going to get funded because I said I'll be very happy if I do 200 parameters in 5 years. Jack Kerouac, very nice quote. Okay, so I got a couple of minutes to go over. I just want to go over a little about I have a whole hour talk on interdisciplinary research. But since we're trying to see if we can do interdisciplinary research, of course, Archimedes, Newton, Gauss, all these people were interdisciplinary researchers. The difference is their interdisciplinary team consisted of one person, themselves. Now everybody wants to do interdisciplinary research. Say, oh, you got to put a team together. You got to put a mathematician, a statistician, an engineer, now maybe a philosopher. My next team will have a philosopher, and things like that. Well, this work, I want to give you a case study, very famous one. It's a sheep farmer's problem. So a sheep farmer has this field and it doesn't have a fence, and he has some sheep there, so he decides he wants to have a fence. And he figures out that he needs to enclose 10,000 square meters. You know, this sheep will have lots of, and he wants to do this as cheaply as possible. And there's a university next to his field. So he walks over there and says, finds some professors and says, can you help me do this? And these sheep will be running all over the university, escaping, so they're very happy. And the sheep farmer also opens the leg of lamb to the person who does the best solution. So he forms a multidisciplinary team consisting of these people. And they all very quickly, they all agree very quickly what the mathematical model for the problem is. What is the shortest fence, the perimeter of the fence, shortest perimeter of a fence that encloses an area of 10,000 square meters. So these people, being professors, are very competitive. So they each try to outdo each other. So they all start. So first the applied mathematician, he remembers his calculus. Aha! I remember that the rectangle with the smallest that encloses a given area with the smallest perimeter is a square. So obviously the answer is a square fence that encloses 10,000 square feet. And that's a side of 100 meters. Notice I'm honoring you by the metric system here. And perimeter is 400 meters, which I write in this curious fashion for a purpose later on. Next comes the philosopher. So he says, wait a second, we all know that this is how mathematicians stereotype philosophers, by the way. We all know that a circle is a perfect geometric figure. So it has to be the best. And in fact, the circle with smallest perimeter, a circle that encloses 10,000 square meters with 355 meters. And it is the closed figure that encloses a given area with the shortest perimeter. It is true. I actually don't know how to prove that. Anyway, so there it is. That's what the philosopher came up with. 400 down to 355. Instead of 200 times the square root of 4, he has 200 times the square root of pi for the perimeter. Now, the engineer is a practical guy. He notices there's a wall over there. Remember, there was a wall. So he says, well, I'm going to take advantage of the wall. I'm a practical guy. So he again does calculus, knows what the area of a rectangle is and stuff like that, and figures out, taking advantage that he doesn't have to worry about a fence on one side, he finds out that the perimeter is from 400 times square root of 2 is now 200 times square root of 2 is only 283 meters. The physicist then says, wait a second, if a circle is better than a square, maybe a semicircle is better than a semi-square. So he says it should be a semicircle, and sure enough, instead of 200 times square root of pi, he has 200 times square root of pi of 251 meters. Then comes the computational scientist. She says, well, just because a circle is better than a square, doesn't mean a semicircle is better than a semi-square. Maybe there's an ellipse that acts, semi-ellipse, half an ellipse that does better. So, and it's a good thing she's a computational scientist, because after some mathematics, she has to solve this problem involving an elliptic integral. PA equals, she has to find the value of A that minimizes this functional. And that doesn't faze her. She's a good numerical person. She has a good method to do that and get that to arbitrary accuracy. So she finds a program and finds an answer. But unfortunately, she finds the same answer as a physicist. So that is good. Well, we only have one person left, the pure mathematician. So after pondering for 2 hours, noticing that the ratio of the 4 answers obtained so far are square root of 4 to square root of pi to square root of 4 over 2 to square root of pi over 2. He only notices that fact. He says to the engineer, physicist, and computationalist, you're all fools. And points to the computational scientists, especially you. You could have all come up with your answers based on the previous answers by symmetry. You double the area, and you do 220,000 square meters, and then by symmetry, that would give you the previous answers, and then you just have it to get to 10,000. But he's not done. He says to his colleague, all of you are fools, because I have a much better solution, which he explains as he snatches the Lego land. So he makes a definition. The outside of the fence is the side of the fence the farmer is standing on. So his solution is to build a fence around the farmer. So it's only 5 meters. So elegant solution, but impractical. Physicist solution, or the computational, is more practical, still pretty elegant. But what's the moral of this example? Just because you put together a multidisciplinary team, people who are experts in one discipline, together, doesn't mean you're going to get good interdisciplinary research. In fact, chances are you won't. Often the team gets the money, and each member of the team runs off to their office, does their own work, and they may advance their own field, but they're not doing anything for the problem that's to be solved. So this is not good enough, and I have 50 more minutes in the talk that tells you what's good enough, but it's basically saying it's good if somebody on the team knows more than one thing. And I was very gratified as we're trying to build interdisciplinary collaborations with philosophers, that if I join such a team, I know zero philosophy, but I'm very gratified that the philosophers seem to know a lot of math. So I think there's a chance for a good interdisciplinary team between math people and philosophers. And since I'm told you have to leave people laughing, this is my last quote. Thank you.
Okay, so we I do want to point out that the perimeter problem is actually known as Queen-Dido's problem.
Yeah.
So there's a classical answer as well.
I added a couple of extra people.
Okay.
I added the wall, I think.
There's the coastline.
Oh,
Make
yeah.
it more,
More rugged.
in the
Right.
mental
Okay.
calculus, but it's still fun. And I wonder if you just build pieces of fence with holes between pieces of fence that are too small for the sheep to get out, you can put even more.
Yeah, but that'll cost you more labor when you build the fence.
Labor's free, but yeah. Okay, real questions, please, for Max.
Great. Perfect.
No comments? Monte experience with Monte Carlo? Anyway, thank you very much then, Max.